Hello everyone. Today I'm going to explain to you how backpropagation works in a neural network and how weights are updated. I think this is important to understand so that at least at a small level, all of us understand what exactly is happening inside the neural network, especially when we talk about forward propagation and backward propagation, because that gives us a little bit of perspective on how things really work for neural networks and that really helps us in understanding the other neural networks that we may be modeling. So at least we approach them not without a blank mind, but at least some perspective on how things work. So in that case, I think understanding backpropagation using a small example is important, and I have referred to some material for this. The description mentions about those sources, both the sources that I have used, and I have tried to, add some of my own details reading from both of these. So hopefully you will find this useful and worthy of your time. All right. So before we talk about back propagation, there is something called as forward propagation. So what happens in forward propagation is that the inputs and weights propagate forward in the neural network so that so this is the hidden layer. So this particular neural network has two hidden neurons in one hidden layer and two outputs. So when we talk about forward propagation, the information from these neurons passes on towards the hidden, and then it passes on to the output layer. So this is how the information is getting propagated in a forward manner. So first, in this, I will write the basic formulas that we will be referring to later on when we talk about backpropagation. So let us talk about the how the inputs are forward propagated in the hidden layer. So at first, what we see is here. So the net of hidden layer neuron H1. So what happens is that the neurons receive the information, they compute some value, and that value is then passed on through a non-linear function to give the information. So that is called as the activation function. So the activation function we have used is sigmoid. So it is generally represented as this thing. So this is the activation function we are using. So this x value is the net activation that any particular neuron receives. So this is the activation that we are computing for h1. So this will be x1. Sorry, this will be x1 into w1 plus x2 into w2 plus the bias term. So these are the in blue. These are the bias terms. So for hidden layer neurons, I have kept the bias same b1, and for output it's b2. So this is how these biases can be different as well. But for the example sake, we are using the same one. So if you look at the values of all these values are given over here. Okay. So when we put on the values, the respective values, we see 0.05 into 0.15 plus x2 is 0.10, w2 is 0.20, and y is 0.35. So when we compute this, this comes around 0.3775. And when we pass this value to this activation function, so it essentially gives us the net output of h1, which is nothing but 1 upon 1 plus e minus net h1. So this is 1 upon 1 plus e raised to power minus 0.3775, which comes out to be 0.5932. So important thing to remember is that this is the final output that this particular neuron H1 will pass on to the next layer. So this is nothing but um, the sigmoid value of this net H1. So these two terms are important to distinguish. So similarly, we compute net H2, and we must remember all these formulas. I mean, not remember, but we will refer them later on when we talk about backpropagation. So this is how it looks. And when we compute it, this becomes 0.05 into 0.25 plus 0.10 into 0.30 plus 0.35, which is the bias term. So this comes out to be 0.3925. So output of H2, like the last time, is 1 upon 1 plus e raised to power minus net H2, and this is equal to 1 upon 1 plus e raised to power minus 0.3925, and this comes out to 0.5968. So these are the two important values in the first iteration of the neural network. So this is output of H1, this is output of H2. So when we look at these weights, W5, W6, W7, W8, these will be multiplied by the output of H1 and output of H1, not net H1. Okay, so this is the final output that the hidden layer is giving us. So then again talking about forward propagation. So these are outputs travel forward. So we compute net O1. So net O1 is output of H1, because this is the value it is transferring, into W5, the connecting waves, and output of H2 into W6 plus the bias term. So this comes out to be 0.5932, because output of H1 we computed was 0.5932 into 0.40 plus 0.5968 into 0.45 plus 0.60, which is the bias term. So when we compute this, this comes out to be 1.10584. So again we squash it using the sigmoid function. So output of H1 O1, sorry, output of O1 is 1 upon 1 plus E minus net O1, which is equal to 1 upon 1 plus e raised to power minus 1.10584, and it comes out to be 0.7513. So this is the output of the first iteration of the forward propagation. Similarly, we compute net O2. Okay, so net O2 is output of H1. So I request you to, when you are trying it yourself, keep the reference diagram handy, so that you can also verify whether or not I am doing it correctly. And it is always nice to do it yourself, then we understand. So, and I myself have tried to understand 4 5 times, and then I have got a hang of it. So moving forward with computation of O2. So this activation value is 1.22484, and the net output. So the output of O2 is one segment of net O2. So this will be minus 1.22484. This comes out to be 0.7729. So this is the first iteration of the forward propagation. We have got output of H1, output of H2, output of O1. So now we have these two outputs, and we have the target output, which is 0.01 and 0.99. So let us try to compute the error for the first iteration. So the error we have used, is mean squared error. So here target value minus output value. So this is how the error is getting computed. The function can change depending on context. So target O1, and this notation is also important to remember. So target output is 0.01, and target O2 is 0.99. So the total error would be error in output 1 and error in output 2, right? So error 1 is half of target value of target O1 minus output of O1 whole square, and error 2 is half of target O2 minus output of O2 whole square. So when we compute it, no, so target O1 is 0.01 and output of O1, as we had seen here, output of O1 is 0.7513. So this is 0.7513 whole square plus target O2 is 0.99 minus output O2 is 0.7729 whole square. So when we compute this value, it comes out to be 0.2983. So this is the error in the first iteration of the back propagation. In my immediately next video, I will show you how this error changes with multiple training times. Using C++ programming, I will show you actually how this changes. So, but in hand understanding, I am only doing it for once. So this is the error for the first iteration error. Iteration error. First iteration error. So ideally this should be minimized. And so now when we talk about back propagation, what we are trying to say is how this error changes with the weights of the network. So what we will be doing is, since all these 8 weights are contributing to the outputs and logically to the error. So in back propagation, what we try to understand is that change, how much delta change in total error is associated with these delta changing weights. So accordingly, we update these weights. So let us try to update the weights in the between the hidden layer and output. Okay. So here, here let me try to say weight update between hidden layer and output layer. So if we look at the weights between hidden layer and output layer, we can see that there are 4 weights: W5, W6, W7, W8. So I will show you how to update W5, and same analogy can be taken for W6, W7, W8. So let us go forward with that. Alright. So let us start with W5. So change in total error due to W5. So this is what we are trying to compute. So what essentially this partial derivative means is that how much the total error changes with change in delta of W5. So this is what we are trying to understand. Okay, so it is also could be called as the gradient of total error with respect to W5. So if we notice, you must, let me just delete this particular thing. Okay, right. So if we notice error total and W5, so if we go back, so error total, so total error doesn't have, it's not a function of W5 directly, so it's output, but indirectly it is a function of W5 because output O1 depends on net output O1 and net output O1 depends on output of H1 and W5. So these are indirectly related. So in order to differentiate, we use a chain rule such that the denominator can be, is able to differentiate the numerator. So what we do is we write it like this using the chain rule. So partial derivative of total error with respect to output O1. So we already know that total error has an output O1 term, and then you know, accordingly we write it like this, and then partial derivative of output O1 with respect to weight 5. So as you can see, this right hand side is equal to the left hand side. The only difference is that the partial derivatives are now, we can now understand how these are, getting, we can understand these values now. So let us compute this first. So partial derivative of total error with respect to output of O1. So, we know what is total error. So partial derivative with respect to output O1 of half of target O1 minus output of O1 whole square plus target of O2 minus output of O2 whole square. So this is our total error. So when we differentiate it with respect to output O1, this will be 0 because there is no term of output O1. So this will be differentiated. So what we obtain is half target O1 minus output O1 into minus 1. So essentially this would be minus of target value of O1 minus output that we had obtained. Okay, and when we compute it, so this is 0.01, so target value was 0.01 and what we had obtained was 0.7513, and this value comes out to be 0.7413. So this is our first term. So we have computed this first term, which is 0.7413. Now we compute this second derivative. So this is partial derivative of output O1 with respect to net output O1. Now if we remember, we had understood that output of O1 is nothing but 1 upon 1 plus E minus net O1. Okay. So let me first simplify it. So if our fx is sigmoid, 1 upon 1 plus E minus x, and if we differentiate our fx, so what we get is, this is essentially differentiation of 1 plus E minus x minus 1. So let us try to first digress a little bit and try to understand it. So when we differentiate this particular term, sorry, when we differentiate this particular term, it it will be minus 1 into 1 plus e raised to power minus x minus 1 minus 1, which is minus 2 into e raised to power minus x into 1. So you may want to visit your fundamentals on derivatives to understand how this works. So this will be e minus x upon 1 plus e minus x square. Okay, so let me play with this a little bit. So I add and subtract 1 in the numerator. So this is how it becomes. And so if I further simplify it, it will be 1 plus e raised to power minus x upon 1 plus e raised to power minus x whole square minus 1 1 plus e raised to power minus x whole square. So this can be further simplified as 1 plus e raised to power minus x minus 1 plus e raised to power minus x whole square. Now if we look at this, so 1 plus e raised 1 upon 1 plus e raised to minus x is nothing but fx. Okay, so this I can write as fx, and this is nothing but fx square. So if I take fx common, so this will be 1 upon fx. So the differentiation of sigmoid or fx when fx is sigmoid is nothing but fx into 1 minus fx. So similarly, differentiate it, when we differentiate it, so because output O1 is nothing but the sigmoid, okay, so when we differentiate it, it will come out to be output of O1 into 1 minus output of O1. Okay, it may sound a bit confusing here, but if you follow this particular approach, because it will be in terms of net output of 1 only, but 1 upon this thing, but this is essentially output of 1. So this is how we write it as, and this value will be 0.7513, which was output of O1 minus 0.7513. So this value is 0.1868. So this is the second term we have computed. So this is 0.1868. Now we compute the last term. So partial derivative of O1 with respect to weight 5, and we know that net output O1. So net output O1 is this particular thing, output of H1 into W5 plus output of H2 into W6. So when we differentiate this with respect to W5, this term cancels out because there is no W5, y is also constant 0. So what remains is output of H1. Okay, so this value is nothing but, so I will write the formula for you. So net O1 is out 1 into W5 plus output of H2 into W6 plus B2. So this comes out to be W, sorry, wrong here. Yeah, so nothing wrong here. So this comes out to be output of H1. So this value is nothing but 0.5932 as we had computed. So error total, if partial derivative of total error with respect to W5 is the nothing but multiplication of the terms where we have computed. So it is 0.7413 into 0.1868 into 0.5932. So this value comes out to be 0.08. Okay. So now how we update W5 is this. So W5 is W5 is the old value minus theta into partial derivative of total error with respect to W5. So this is called as the learning rate. Okay. It ranges between 0 and 1. So better to take a small value so that you can learn in small step, but not so small that you keep on learning. So in this particular case we have taken eta as 0.5. So in my next experiment I will also show you how this changes as eta changes. So W5 is 0.40 minus 0.50. So this is our old inherent weight, and this is 0.082. So 0.40 minus 0.041, which is equal to 0.359. So this is the updated weight of weight 5 after first iteration. So similarly, we can compute for W6, W7, W8. For your reference, I will write the formulas here so that you can try in your free time. So this total by W6, can be total partial derivative by output of O1, then this output of O1 with respect to net output O1, and then this net output O1 with respect to W6. So this is how you can compute for W6. Similarly for W7. So this understanding of partial derivative, which term to use, which not to use, will be clear if you look at the definitions of the various values we are computing. So this will be output of O2 because W7 goes indirectly in output of O2. So we are differentiating it with total error with respect to output O2 because later on net output O2 is actually a function of W7. So this is how we do. And then similarly for W8, it will be like this. Partial derivative of total error upon output O2 2. So you can also notice a bit of symmetry between W7 and W8 and W5 and W6. So this is how you go about it. And if you compute it, you will see that W6 comes out, the new weight comes out to 0.40867. W7 comes out to be 0.5133 and W8 comes out to be 0.56135. So these are the updated weights and W5 of course was 0.359. So what we have been able to do is we have updated these set of weights now. But there are other set of weights also that need to be updated. Okay, so then we will backpropagate further. But all the weights are changed only after the entire backpropagation has been done. So even though when we update for W1, W2, W3, W4, we will need these weights, but we will not be using their updated weights, because when we are trying to learn the weights, these old values are only back propagated. Only after all of them have been updated, then we start off fresh in a second iteration with a new set of weights. So for updation of W1, W2, W3, W4, old weights only will be used. Once all these 8 weights have been found, the new weights, then all of them are updated and the second iteration starts. So I'll just add one more. Yeah. So this is a back propagation between hidden and input layer. Okay. So essentially what we are trying to do here is how the total error depends on these set of weights and how the delta change in total error varies the delta change in each of these weights. The important thing to remember is that W1 is being fed to this particular neuron H1, and then this H1 output from H1 is going to both outputs O1 and O2. So definitely this W1 is contributing to both the errors, E1 also and E2 also, which was not quite the case in W5, W6, W7, W8. W5 was only linked to output O1, so it was only affecting E1 part of the total error. However, when we talk about W1, it is impacting both E1 and E2. So this thing needs to be taken care of while updating the weights between hidden and input layer. So, so let us start. So we move forward with updation of the weight between hidden and input layer. So I will show an example for W1. So we can write this as output of H1 into partial derivative of output of H1 net output of H1 and then partial derivative of net output of H1. One question that can emerge is that okay, how do we understand how to differentiate this with which particular variable, especially in chain rules? I would say you start off with what seems suitable to you. Gradually, we will arrive at this. So I'm writing it directly, but even if you go with output of open, and gradually you will arrive at this particular thing. So this we already know. So this is nothing but output of H1 into 1 minus output of H1. Okay. And this particular thing, so net H1 with respect to W1. So if you look at net H1 with respect to W1, it is X1. So good one. So this is X1. The only thing we X1. Sorry. The only thing we need to think deeply about is this particular term. So majority of this portion will consist of understanding this one. So total error, is E1 and E2, and as I've already mentioned that W1 is contributing to both E1 and E2 because it is, connected to H1 and H1 is connected to O1 and O2. So E total is nothing but E1 plus E2 out H1. So what we'll do is we'll separate this and compute them separately. Plus E2 upon output H1. Okay, just simplifying it. So now let us first look at this term. So partial derivative of E1 with respect to output of H1. So using chain rule, we can write it like this. Net O1 by partial derivative of output of H1. So this, if you differentiate even with respect to output of O1, this will come out to be minus target O1 minus output of O1. This is how it comes out. Partial derivative of output of O1 with respect to net O1 is nothing but output of O1 into 1 minus output of O1. If you are confused about this, just check this out. We already computed this value. So net output, partial derivative of output of O1 with respect to net output of O1 is this by this particular thing that we have understood. And partial derivative of E1 with respect to O1 is nothing but partial derivative of total error with respect to O1 because O2 is essentially 0. And net output O1 with respect to output of H1. So partial derivative of net output of O1 with respect to output of H1 is W5. So this is W5. So when we actually compute this value, it comes out to be 0.7413, which is this particular value, into 0.1868, and W5 is 0.40. So this value comes out to be 0.05538. Don't get confused, this particular value, we have already computed an output of O1 multiplied by 1 minus of output of O1. Also, we have computed here 0.1868. So I'm just using the value we have already computed. So this first portion is 0.05538. Now we compute this second portion. So when we talk about the second portion, partial derivative with respect to output of H1. So again this would be E2 with respect to. So here what we do is we try to understand how to go about this. So error 2 has output O2 and partial derivative of output of O2 with respect to net O2 and then net O2 by output of H1. So this particular value, partial derivative of error 2 with respect to output of O2 will be minus of target O2 minus output O2. Then second derivative would be output of O2 1 minus O2 using the sigmoid differentiation function, and partial derivative of net O2 with respect to out of H1. So net O2 with respect to output of H1 is nothing but W7, and W7 is 0.50. So this is W7. Okay, so when we compute this, this will be minus of 0.99 minus 0.7729, then 0.7729 multiplied by minus 0.7729 multiplied by W7. So when you actually compute it, this value comes out to minus 0.01905. So what we have found out here is that D is 1 upon the output of H1 plus partial derivative of output with respect to output of h1, which is nothing but 0.05538 plus minus 0.01905, which is equal to 0.03633. So this particular term now we have computed 0.036. Okay, so this we already know, and this is x1. So now we can say that partial derivative of total error with respect to w1 is 0.03633 into output of h1, 1 minus output of h1 and x1. When we compute this, this will be 0.03633. Output of h1 is 0.5932. So this will be 0.5932. And x1 is, what is x1? X1 is 0.05. So 0.05. Okay, so this is how it comes out to be. So this value comes out to be 2.19 into 10 to the power minus 4. So now we update W1. So W1 is W1 minus eta into this term we have computed. So this is W1 is initially 0.15 minus 0.5 into, this is the learning rate, 2.19 into 10 to the power minus 4. So when we compute this, this comes out to be 0.14978. So this is the updated weight. This is the updated W1. Similarly, we can compute for W2, W3 and W4. So I will just write reference formulas for you. So to compute updated W2, you can calculate gradient like this. So again, little bit of symmetry here as we had seen in the previous when we were updating weights between hidden and output layer. This takes a little bit of practice. I think with 4-5 times also I am still learning how to do it. So and then total with respect to W3 is equal to, so again here for each of these chain derivative, you will have to further split these first terms. Rest is very easy. So I encourage you to try it with your hands because it is really very interesting and very good exercise in clearing our fundamentals of calculus and linear algebra as well. So I highly recommend you to understand this because this makes you more confident also while you're working on neural networks and trying to model it, because then you are not exactly clueless. You know at least something what is going on. So this is extremely important to understand, and with practice I think it's not very difficult to understand this. So these are the formulas you can use for, and then this again you can split like how I've explained over here. So when you're done with this, you will see that the updated W2 would be 0.1995. W3 would be 0.24975 and W4 would be 0.2995. And previously we had calculated these updated weights 0.3589, 0.4086, 0.511 and 0.5613. So these are the updated weights in the first iteration. Okay. So similarly, you know, and this goes on. And if I encourage you to compute error to, by these set of updated weights, just try to see how the error is decreased, and you will see that as the weight gets updated, the error decreases, and that's the whole point, to improve the predictability, improve the neural network such that it is able to converge to the output but not overfit. So I just attempted to explain to you the back propagation, and in my next video I want to show you a C++ program in which I have tried to do this for propagation and backpropagation. And because of the power of computer programming, I will also show you uh, training multiple times, and then I will show you how error is changing, and I will do a little bit of experimentation with the learning rate as well. And yeah, so that would be, I think, another useful experience for you to understand deeper how neural network work. I understand that this video is not perfect and there might be some inconsistencies and glitching in my way of rendering. So it would be really nice if you can comment upon and let me know how I can improve. Thank you so much for your patience.